So in this video we're going to introduce the spherical coordinate system. And the spherical coordinate system is called the spherical coordinate system precisely because it is kind of an optimal system for describing points on the surface of a sphere. But if we just kind of extract it out and not look at a surface of a sphere and think about what the spherical coordinate system is, it's pretty easy to wrap our heads around it. We're going to have theta being the angle that's made with the positive x-axis. So this is the same angle theta that we had for cylindrical and polar coordinates. And then we're going to have an angle phi that we make with the positive z-axis. So phi is going to be an angle that runs from 0 to 180 degrees. And then we're going to have rho, which is just the length of the line segment from the origin to some point P in space that you're trying to describe. It is not uncommon in both math and physics to use r instead of rho to represent the length of that radius, but frequently in math you're going to see rho used instead of r so that we don't confuse it with the r that we get from cylindrical and polar coordinates, where we let the length of this line segment in the xy plane be represented by r, and we get that relationship r squared equals x squared plus y squared. So it's common in math to replace the r with the Greek letter for r, rho. And then some other conventions that are different in math and physics. In physics, they'll let this angle be the angle phi, and this angle will be the angle theta. So they'll reverse those two angles. So just things to realize when you're looking in different books. You can see rho theta phi, you can see r theta phi, you can see r phi theta, just depending on what the convention is for that particular text. Relationships between rectangular and spherical coordinates are fairly easy to come up with. So if we kind of expand this picture, and then again we're going to use the convention that this radius is called rho, and that the distance from the origin to the point in the xy plane directly below the point P, we're going to let this distance be the distance r. So we know that from our previous work that we've done that r squared is going to equal x squared plus y squared. So if we think about what's going on here, we've got some claims going on. Rho squared equals x squared plus y squared plus z squared. Well, rho is just the length of this line segment. That's all that it is. And this is a dropped perpendicular to the xy plane. So this is actually forming a right angle here. So if this distance here is r and this distance from here to here is z, then the Pythagorean theorem would indicate to us that rho squared, this length, the hypotenuse squared, would be equal to the sum of the squares of the legs of the right triangle. But r squared, from previous work, we know that's just going to be equal to x squared plus y squared by the Pythagorean theorem. So we can replace the r squared with the x squared plus y squared, and then we get plus z squared. So this first relationship just comes to us directly from the Pythagorean theorem. Because theta is the positive angle we make with the x-axis in the xy plane, we're going to get that the tangent of theta is equal to the side opposite over adjacent. And because this theta is the same theta that we've used in both polar and cylindrical coordinates, this relationship is one that we've already seen. So the other claim is a claim about the angle phi right here. So we're making a claim that the arc cosine of z over p equals phi. I think it's easier to attack this from, hey, what is the cosine of that angle phi? I have a hard time drawing the fancy phi, so I don't usually try to draw fancy phi because I mess it up. But at this distance here, r in the xy plane, we can bring it up and form a rectangle. And if we do that, this distance is still r, and what we want to recognize is that the cosine of this angle is going to equal, this would be distance r, and this distance right here, forming this right triangle, this distance from here to here is going to be the distance z. So the cosine of phi is just going to equal z over the radius, and the radius is rho units long. So we get z over rho. But rho squared is x squared plus y squared plus z squared. So if we want to know the length of rho, we take the square root of both sides. So we could replace rho with the square root of x squared plus y squared plus z squared. And then, of course, if we wanted to solve for phi, we would just take the arc cosine of both sides. And that's what's been done here to dig the phi out of this. So it's just coming, these relationships are just coming to us directly from trigonometry and are very easy to justify using a combination of the Pythagorean theorem with right-angled trigonometry. So we get a few more relationships as we want to convert from spherical to rectangular. So the claim is that x is equal to rho sine phi times the cosine of theta. And again, this is pretty easy to justify. So if you just focus on x in the xy plane, we know from trigonometry that if this right here is r units long, the hypotenuse is r units long, we know from trigonometry that x equals r times the cosine of theta. And we've already seen this show up in polar and cylindrical coordinates. So then, just like we did in the previous slide, this is a right triangle here. We can bring this length up so that the right triangle is here instead. And then we can think about, well, what's this distance right here? This is the distance rho. And this is the distance r. And what does r equal? Well, r equals, in terms of the angle phi, r is the side opposite phi, so it would be opposite over hypotenuse. So the sine of phi, what we want to recognize is that r is going to equal rho times the sine of phi from right triangle trigonometry. Sine phi, I'll do the sloppy phi. So then you can just make a replacement. This r can be replaced with rho times the sine of phi times the cosine of theta, and you get the relationship that's right here. And then you would play the same game for y. We already know that y equals r times the sine of theta from work we've already done and from right triangle trigonometry. But we just established that rho is equal to rho sine phi, so you replace r with rho sine phi, and we get rho sine phi sine theta is our y coordinate. And then z's going to be relatively easy to justify because we have z as the side adjacent phi, so we know that the cosine of phi is going to equal the side adjacent phi over the hypotenuse, which has length rho, and then we'd multiply both sides by rho to isolate the z coordinate. So z is going to equal rho cosine phi. So those are in spherical coordinates, the relationships between spherical and rectangular coordinates.